Okay, let's start. So welcome guys, welcome back to NEET World. So in this class we are going to start with the physics topic, and the topic which we have left is work, energy and power. In last class we have started with the question, that is an object is displaced from a point A and B by applying a force F is equals to xi plus 2yj. So this was the last problem which we have seen. So the next topic which we are going to see is the potential energy of a spring. Okay. So when we are talking about spring, we know that if we extend spring or if we compress spring, what happens? It will come to original position, right? No, it's come to original position. So in this thing, no, a spring was there. Now if I try to extend the spring and keeping some point, keeping at this some point, what happens here? What energy we can say? Like some potential energy is there, no, like stored energy. If I leave that, what happens? It will convert to kinetic energy. Same thing, if I press that spring, what happens? The potential energy. If I leave that spring, again kinetic energy, right? No, it will oscillate and it will come to neutral point again. Yes, no? So that neutral point is nothing but equilibrium position, we'll say, no? Yes, no? Equilibrium position, where it will be in the original length, right? No. So here if I compress it, what happens is F is negative. If I extend it, F is positive. Okay. And one more thing, whenever I extend or compress, it directly depends upon the force. Yes, no. If I apply less force, the compression or extension will be less. If I apply more force, compression or expansion will be more, right? No. So we can say that F is directly proportional to x, no. Is this x is nothing but compression or expansion, no? Yes or no? This compression or expansion we can say. So the formula of the spring force is F is equals to minus kx, right? Now if we want to find what is the work done by the spring, we know that work done is equals to force into displacement, right? So in here we are talking about x as a displacement, right? Now so when we talk about work done, so W is equals to integral of 0 to x f dot dx. Okay. So here the x will be the compression or expansion. So and the force is nothing but minus kx. So what is k here? Constant. K is spring constant. K is spring constant. Okay, no? So I can take the k outside. If I integrate x, what happens? X is square by 2. So the final will be minus kx x square by 2 from 0 to xm. Okay. So if I substitute the value, it will become minus kxm square by 2. Okay. So this is my work done by the spring. So whenever if a graph is given between force and a displacement, okay, if I find the area of that, I can get the work done, no? This is the thing we have seen in the work done also. In the previous thing, like normal work done, if we take the graph and if I find the area of this graph, I can get the work done. Okay, you can take a note of this. Done. Can we go for the next one? Completed? Okay. So if we see here the potential energy of a spring, a block is moved from an initial displacement, that is x initial, to the final displacement xf. Okay. So now what happens here is the work done by the spring force is nothing but work done integral initial to final minus kx dx. The same thing right now. What we have taken in the previous case, this was the initial case, that is x equals to 0, right now x equals to 0, either I have compressed or expanded, which is nothing but x or x we have considered. Now what is the thing we have done here? So initially there was a place, now I have extended or compressed, whatever it is. Now the final displacement is there, initial displacement and the final displacement. Okay, simple thing. Let me consider this was the initial position of the spring. I have taken the spring to some point and I am keeping over there. Again I am expanding. Now what will be the work done for this particular point? Got it? So this one can be considered at 0 and this is x initial and this is x final. So from here to here some work done will be there, and from here to here again some work done will be there. Got it? So what we can do here? Integral x initial to x final f into dx. So f is nothing but minus kx. So if I integrate this, what will happen? Minus k x square by 2 from x initial to x final. Now if I substitute these values, no, so minus k x final square by 2, again minus of minus k x initial square by 2. So what happens here? This minus and minus will become plus. So k x initial square by 2 minus k x final square by 2. So this is my work done for the given particular points right now. So here if I take the negative sign inside, no, it is plus and it is minus. The value what we got are same. Okay, you can take a note of this. And one more point is, the work done by a spring force depends only on the end point. If the end point is known only, I can say what is the work done happen over there, no. And one more thing is, work done for the spring is conservative, like force is conservative, spring force is conservative. For example, how can I say is, some energy was there initially. If I try to expand, no, that energy has been converted either into kinetic or potential. Okay, so conservative is nothing but initial and final point. It depends only on initial and final point. You can take a note of this. Once you have completed, we can go for the next one. Done. Can we go for the next one? Done. Okay. So the next one is, yeah. So if I see here, the total mechanical energy will be equal at the initial point and the final point, right? No. So initially it was like this, no? Okay, it was like this. So what I can say, some potential energy was there. If I try to increase, no, increase or decrease, like expansion or compression happen. What happens here? Some part of this potential energy converted into kinetic energy, right? No. So initially there won't be any kinetic energy because it is in the stable position. It won't move. It is stationary. No, it won't move, right? So potential energy will be there. So when it starts moving, the potential energy will be converted to kinetic energy. I am not saying like almost every potential energy convert to kinetic energy. So when I try to move, it will convert to kinetic. Okay. So can I say like this? So mechanical energy initial will be equals to mechanical energy final. So mechanical energy initial will be equals to mechanical energy final. So what is mechanical energy? It is sum of potential plus kinetic, right? So kinetic energy initial plus potential energy initial will be equals to kinetic energy final plus potential energy final. So this is the thing. Initially kinetic energy, no, 0. Potential energy of kx square will be equals to of mv square kinetic energy plus of k x1 or x final square. This is initial and this is final. Okay. So from this I need to find what will be the value of velocity. Okay. So kinetic energy will be maximum at the equilibrium position, that is x equals to 0. So if x equals to 0, what happens? Of kx m square will be equals to of mv square. So from this it is 1 by 2 will get cancelled off, and so velocity vm square will be equals to kx square by m will be there, and if I take the under root of that, under root of k by m into x, so this is my velocity. Okay, take down. So the worksheet has been given now for the homework. Try to fill that worksheets, okay? So whatever the work you are doing daily, try to fill it. Which one, sir?
Half into kx final square. Neglect. Why did they neglect?
So the thing is, this is the
Final position.
equilibrium position, no? Equilibrium position. Here what happens here?
Potential
X will be 0, right? No, x will be 0, and in this case what happens here?
X will be any number.
Like x will be any number. What here? X will be 0, and in this case velocity will be 0. Here I am started moving, so velocity will be there. At this point velocity becomes 0 at final point. In this point like x will be 0, so the substitution I have taken here. Got it? Done. So here is the graph between the total energy, kinetic energy and potential energy. Okay. So what we can understand here from the graph, this is
If
K is max, V will be 0. If V is max, K will be 0, which means like when it's try to decrease, I mean potential energy tries to decrease, kinetic energy try to increase. Similarly, kinetic energy decreases means potential energy increases. At some point, potential energy will become 0, kinetic energy will become maximum. And one point, potential energy will become maximum, kinetic energy will become 0. So when I take, the total energy will be always same. Okay, it will be constant.
Total mechanical energy.
Yes.
The point where the intersect is potential energy will be equal to kinetic energy.
In this point, yes, where the point get intersect, that point is potential energy equals to kinetic energy.
This graph was given for a different example also.
Which,
Pendular.
Projectile.
yes.
Pendular కూడా right.
Because it's like oscillation only now.
Done.
So in basic math, we have seen about maxima, minima condition, no? So what is, how to find maxima or minima of the values of the equations? So the first thing is, we will write the equation. For example, equation has been given, right? No, equation has been given. If I differentiate that equation, I'll get like dx something, du by dx, I'll differentiate and I equate to 0. This is the first step I'll do. So whatever the value for x or anything I'll keep as it is. Second step, what I'll do, I'll double differentiate. Yes, no? Double differentiate this. So whatever the value of x we got, we'll substitute here. Right, no? If we get negative value, it is maxima. Okay, the equation will be maxima at the particular point. Suppose another number is there. If I substitute this value, I am getting positive, which is minima. Right, no? Minima. So if I get a if I want to get maxima, the value should be negative, which means at that point the equation is maximum. Okay. If I get a positive value for some particular point, I will get minima. Okay. So similarly, in this case, no, whether if I want to find equilibrium or stable equilibrium or unstable equilibrium or neutral, the same steps we are going to follow. Okay. First differentiate, equate it to 0 and double differentiate, whatever value we are getting, we will substitute those values here. Okay. And here the slight changes happens here. Okay. So we will see that now. First thing, conservative force and potential energy. What is the relation between the force and potential energy? Okay. So conservative force is one where work done by the force does not depends on the path, only the initial and the final position. This is the thing we have seen, no? Spring force, only the initial and final position, right? No? So example, gravitational force, electrostatic force, spring elastic force. Okay. So the relation between the force and the potential energy is nothing but F is equals to minus du by dx. If the equation is given, u is equals to some equation has been given for the potential. If I want force, what I should do? Differentiate.
By
Okay, differentiate with respect to x or whatever the terms they have mentioned there. Okay, I will get the force. Okay, this is the force. So force equals to negative of the rate of change of potential energy with position. Okay, so the negative sign shows that force always acts in the direction of decreasing potential energy. Okay, take down. Done. Can we go for the next one? Done. So in vector form, like in the direction of x, y and z, which is nothing but f is equals to minus dou u by dou x, dou u by dou y, dou u by dou z. Okay. So it's a partial differentiation, we'll say. Okay, partial differentiation. Like equation has been given in terms of x, y, z. Okay. If I want to differentiate with respect to x, I'll keep y and z as it is, I'll differentiate x. For y, again I'll keep x and y, so x and z as it is, I'll differentiate y, and for z, x, y I'll keep as it is, differentiate z. Okay, partial differentiation we'll say. We'll go for the problem. We'll do problems now. Yeah. So before that, okay. So before that, we'll see the types of equilibrium. Okay. So stable equilibrium, unstable equilibrium, neutral equilibrium. Okay. So first one is stable equilibrium. The steps I have told now. First thing what I should do, if u is given, potential is given, okay, I need to differentiate. This is the first step. Then double differentiation. So du by dx, this is the first step. Second step is d square u by dx square. Before that, what I should do in the first step, equate it to 0. I need to get the value of x. Okay. So in the second differentiation, need to substitute the value of x. If I get positive, it is stable. In the maxima or minima, if I get negative, it is maxima. If I get positive, it is minima. But quite opposite here, if I get positive, it is stable equilibrium. If I get negative, it is unstable equilibrium. If I get 0, it is neutral. Okay, it is not stable, it is not unstable, it is neutral. Okay. You can take a note of this. Completed? Can we go for the next one? So for the unstable equilibrium, same, du by dx will be equals to 0, and I'll keep x values and substitute in the second equation. If I get the negative, it is unstable. So similarly for the neutral equilibrium, I'll take the first step as it is, I'll get the values of x. If I substitute the values, if I get 0, it is neutral equilibrium. Okay. Done. So we'll see problem now. Now, so calculate the work done by the force F is equals to y I cap to move the particle from 0 to 0, sorry 0 comma 0 to 1 comma 1 in the following condition: y is equals to x, y is equals to x square. Okay, they are asking what is the work done for the force F is equals to y I cap. Okay, so what I should do over here now? Work done will be equals to integral of x initial to x final f dot dx, right? No, so what is f here? Y axis, I mean y is the variable they have given. What is y? I should take either x or x square. For two conditions I should take. Okay, and I cap they have mentioned. So I cap in the sense in x axis. So 0 to 1. So 0 to 1 y, so x no, with respect to dx no. So x dot dx. So what will be the answer for?
Square by 2.
Yes, x square by 2 from 0 to 1, which is nothing but 1 by 2 minus 0, 1 by 2 joules. For the first question, what is for the second question? This is the first one. Second one will be
X cube by 3.
okay, x cube by 3, which is nothing but 1 by 3 joules. No, okay, we will find it. So work done will be equals to x initial to x final f dot dx. What is y now? F is y equals to x square. So from how much? 0 to 1. 0 to 1 x square dx. If I integrate this one, x cube by 3. So x cube by 3 from 0 to 1. So 1 by 3 minus 0, which is nothing but 1 by 3 joules. Okay, you can take a note of this. Done. Okay. See, here is the question. A long spring, when stretched by a distance x as the potential energy u, increasing the stretching to nx, the potential energy of the spring is. So what is the formula for the potential energy?
Kx square by 2.
Of kx square. Yes, kx square by 2. 1 by 2 kx square. So this is initial. Yes, no. Distance is x. Okay. This is the formula. Now what they are saying? Extended to nx, which is nothing but u final will be equals to of k into nx the whole square, right? No, nx the whole square. Now if I see here of k n square x square. So when I see over here, no, this is initial of k x square. Can I substitute that value? N square into u initial. So the answer is n square u, option C. So in terms of initial they have taken. Okay, no? Done? Okay. So with this I'll stop the class. We'll see the next part of the problems in the upcoming sessions. Okay, you can wind up, guys. Thank you.